Hello, everyone. Welcome to my session. I'm Xiaoyue, technical artist from Epic Games China. I've been with Epic's dev relations team for nearly 4 years now, and my work mainly focuses on VFX and chaos physics. Helping Chinese licenses sort out their issues when they are using Unreal. And for today's session, I'd like to share some tips and tricks for class dynamics. Let's dive right in. Okay. Since 5.3, a new panel-based class editing workflow has been introduced. And with the latest 5.6 release, Chaos class has improved a lot, both in features and performance. I've always been very interested in our physics engine, so I spent some time learning how class works and ran some tests, especially based on common questions I've heard from users in China. So for today's agenda, I'd like to show you how to work with this new workflow and share what I've learned about Chaos class, both in terms of art direction and runtime stability. And I'll also talk about some advanced features in the end. Many of you are probably familiar with this traditional class workflow, the one embedded inside the skeletal mesh editor. That setup still works, but it does have some limitations. For example, the class data is created per material section, which means different material parts won't interact or self-collide. That can be tricky when your outfit has multiple materials. Also, as you probably know, many physical properties can be adjusted by mask painting. But painting in this 3D window isn't ideal. The brush tool can feel a bit limited in that context. The new panel-based workflow introduced a new standalone class asset. It's decoupled from the skeletal mesh editor and built using the data flow graph, which is a non-destructive node-based configuration system. To help artists get started quickly, the editor generates a template whenever you create a new asset. It has all the key nodes already connected, along with some tips and comments to guide you through. And of course, you can't call it a panel-based editor without a 2D class panel. This will make painting much easier and feels more similar with other external DCCs like Marvelous Designer. Speaking of Marvelous Designer, the workflow between it and our panel class is quite smooth now. If you export your class as USD in Marvelous and check the include simulation data box, you won't just get the model itself. Lots of the physical settings will also come across. That means better consistency between what you saw in Marvelous and what you get in Unreal. Now I'll quickly walk you through the basic 1, 2, 3, 4 steps that are already marked in this template. Okay, so after importing your model, the second step is skinning. Panel class includes an auto skin transfer node, which lets you transfer it directly from the character's body mesh. I'll go into more detail on that later. Next, we paint the max distance. A value of 0 means this part is kinematic. It will stay fixed to the animation. And the non-zero parts are dynamic, and we define how far each vertex can move away from its animation. Once that's done, the class starts simulating. But at this point, it's not interacting with the body. So for the final step, we assign a physical asset, which provides collision shapes that fit our mannequin. Now we have a basic working setup. Of course, depending on what you are targeting, game or cinematic content, there are a lot of optimizations or improvement beyond that. Because the model I just showed is pretty simple, I actually skipped one important step, which is separating your render mesh and your simulation mesh. In real-time applications, what we render and what we simulate are often based on different meshes. The render mesh has more details, and it often includes parts that don't need to simulate, like pockets, zippers, or small decorative parts. The sim mesh, on the other hand, usually prefer a cleaner and more uniform topology, and we usually need to cut down the poly count heavily. In game productions, this often involves a lot of manual work. Artists will hand place the edge flow and only preserve details where it's really needed. In practice, you can import your sim and render mesh separately, and then use the merge collection node to combine them together. Since I'm not a modeler myself, when testing my class, I used the built-in remesh node to simplify my sim mesh. I actually found it quite convenient, and it now supports adaptive remeshing. So you can paint a mask to control where you want more mesh density and where you want less. A simple example here, I reused the mask I painted for max distance to drive the remesh density. And you can see the purple kinematic area are cut down more heavily, which makes sense because it's a fixed part. By default, the render mesh is wrapped onto the sim mesh based on its position in space. And for simple cases, that works fine. But with more complex garments like this baggy sleeve overlapping the torso under the armpits, or if you can imagine a belt resting on top of a coat with some overlapping area. Oh, sorry. You need some manual isolation to keep things clean. That's where the proxy deformer comes in. It works by grouping different parts into selection filter set. Each render mesh selection is only influenced by the corresponding sim mesh selection. That gives you more control over how the render mesh is deformed. Okay, that's the introductory part for the basic workflow. Now let's talk about the artistic side of simulating chaos claws. I'll focus on two questions here. First, how do we set up claws that's made of different materials? And second, how can we guide the simulation with character animation and external forces? Here, I cached 3 cloth simulations that are set up differently for silk, cotton, and leather. As you can see, they move in very distinct ways. From left to right, silk feels more light and soft with lots of fine wrinkles. Cotton still feels soft, but with fewer wrinkles. And on the right, leather shows some bending resistance, and it can even feel a little stretchy. All of these differences come from a combination of density settings and each material's stretch and bending properties. Let's take a closer look at the keynotes for different material properties, the 3 I highlighted in this picture. First, the stretch config. It builds distance constraints along the edges of the mesh, and each edge will try to maintain its original length during the simulation. That's how claws resist stretching. Next is the bending config. It creates bending constraints between neighboring triangles, trying to preserve their original angles. That's how claws resist bending. And finally, the mass config affects how heavy the cloth feels, which influence how it reacts to forces and how it collides with the body. Here I listed the parameters I used for the 3 fabric types, but I don't want you to treat them as a preset, because in real productions, things like the mesh scale, the mesh resolution, your frame rate, and your solver iterations, all these things will affect how cloth behaves. So these are just the numbers that fit my scenario. But the takeaway here is you should look for real-life references and understand what each parameter does, and make sure different materials on your outfit feels different in motion. Let's take a closer look at the constraints. We support two types of constraint, PBD and XPBD. PBD is faster and more game-targeted, while XPBD is more expensive per iteration, but it provides more physically meaningful parameters, and it gives artists more control. I've listed their main differences here, and there are a few things I want to highlight. First, the unit of stiffness are different. PBD uses a scalar between 0 and 1, and XPBD, on the other hand, uses Newton per centimeter in Unreal. And when using XPBD, the stretch stiffness is usually much higher than the bending stiffness. Think about how much effort it takes to fold a place compared to pulling it in real life. From my experience, it's very common to set the bending stiffness to something like 0.1 or 1, while the stretch stiffness can easily go from hundreds to even thousands. Another thing about XPBD is we also have damping on constraints, so you can control how quickly the constraint settles and stop oscillating. And XPBD also supports anisotropic stiffness, so you can set different stiffness values vertically, horizontally, and along the diagonal. Bending constraints are a little more complicated than the stretch, but a lot of the differences between materials really show up in how we set up the bending, so I'll talk more about it. There are also two types of bending constraints. The face spring works by creating a distance constraint across the neighboring triangles, while the hinge angle resists bending based on actual angular changes. Generally speaking, the hinge angle is better at holding certain angles and maintaining the whole structure, but it's also more expensive. When using the hinge angle, there's another setup I find very interesting for representing different materials, which is the buckling stiffness and the buckling ratio. These two parameters help control how fabric folds and wrinkles. When two neighboring triangles bend beyond a certain threshold, the solver switches from using the normal bending to the buckling bending stiffness. And with a lower buckling stiffness, the fabric tends to collapse more easily and stay in a folded or buckled state. You can see the effect of buckling in the videos here. For soft fabric like silk, I usually go with a higher ratio and a lower buckling stiffness. But for fabrics like leather, it's harder for them to stay folded, so they usually have a low buckling ratio and a relatively higher buckling stiffness. After setting up different materials, another thing I want to talk about in terms of art directing is the animation following. For cloth simulation, especially when it's on characters, the dynamic behavior is driven by the underlying animation. we pin certain part of the class directly onto the character, which, as I mentioned before, is the kinematic part. And then we blend smoothly into the simulation. And we have to make sure it won't drift too far. Good animation following starts with good skinning. I want to highlight our skin wave transfer here. It uses a more advanced transfer method called implant mask. By default, it first copies or transfers the weight from the body to nearby points, and then derive and fill in the rest. In most cases, it gives smooth and reliable result. But if you look at some loose areas, like the hem of the skirt or some tight concave areas, like the armpits or behind the knees, those areas are more challenging and may need some extra work to get a smoother result. Here's a small tip to improve those areas. You can manually mark them using a mask and tell the transfer tool explicitly that this region shouldn't get transferred directly. They need to be derived smoothly from the surrounding surface. And here you can see the difference. With the help of an extra mask, the result looks much better. From the skinned kinematic part, we transition to the dynamic part. There's a common issue I want to talk about in this area. Most of the time in game scenarios, they use simple capsule collisions, and they don't always match the actual body mesh very closely. Sometimes you'll see a sudden pop in the transition area because the vertices get pushed out suddenly by the coarse collision once they become dynamic. So here's another tip. The skinning blend node outputs a weight map that indicates which part of the render mesh is skinned and which part are deformed by the simulation. And the nice thing is this map can actually be further edited to help smooth out the transition. So here, as you can see, I repaint the same map after the skinning blend node, and it's a weight map on the render mesh. I smoothed the cuff area, make it blend with the anim position a little bit, and you can see the result after. Skinning blend lets you blend with the anim position directly on the final render mesh. But we can also build connections to animation on the simulation side. Anim drive is a node that creates spring constraint from each dynamic vertex to its skinned position. In this example, my dress have a plated design from the waist down, so I paint a gradient here. It smooths the transition from kinematic to dynamic and help keep those folds in place during the simulation. Okay. Apart from helping with the transition, anim drive can also guide tricky movements. For example, this long cape here, when the character crouches, I lifted the cape bone a little bit and amplified the anim drive. That way, it won't get tangled around the heels. Because you only need to amplify the anim drive when the character crouches, you'll need to adjust the parameter at runtime. In fact, most physical properties support runtime adjustment. You can access them through the class outfit interactor, which is a new interface compared to the old skeletal mesh class. Here, I want to mention that when you are setting these parameters, you can right-click on a node to copy interactor name directly and paste it in the blueprint function after. One last thing I want to talk about in art directing is the wind setup. Chaos clause has a pretty realistic aerodynamic effect with separate control for drag and lift. If you want your clause to move more stable and move more in line with the wind velocity, you need a higher drag. And if you want to inject more energy and make it turbulent and flatter, you want to increase the lift instead. And on the aerodynamic config node, we also have a outer drag and outer lift parameter. They separate the wind's effect on the front and back side of the clause. So if you dial down the outer drag and outer lift, you reduce the wind force that pushes the clause towards the character's body, and that can help prevent clipping in some cases. Okay, let's move on to the second topic today, runtime stability. This is important because, as we all know, in most game scenarios, clause has to meet the frame time budget first, make sure it stays stable during gameplay, and only after that, we aim for realism. I think the most important issue we face at runtime is clipping. It usually happens when characters move quickly. The collision body moves too far within a single frame, and the penetration can't be resolved in time. Ultimately, as you probably know, we need more sub-steps to solve that. But to be honest, in most game scenarios, we just don't have enough budget for that. So the question people care more about is, how do you prevent clipping at a low budget? One of the most useful tools here is the backstop. What it does is it places a sphere behind each vertex based on its skinned position and limit how far each vertex can go backward along the normal. It's a per vertex spatial clamp, not real physical collision, so relatively it's quite cheap and stable in terms of performance. One thing I want to stress about the settings here is the backstop radius. Since it's a per vertex clamp, the stopping only happens around around its own sphere, so you need to make sure the radius is large enough. Otherwise, it might get around very easily. In general, the further the backstop distance, the larger the backstop radius should be. And you often need to paint these values based on how loose or tight different parts of your clause are. And there's another issue I want to mention. Backstop is perfect for tight outfits, but for baggy outfits like the skirt here, because the skinned ending mesh is quite far from the actual leg, using the skinned position to block movement can sometimes look unnatural. It might feel like there's something invisible behind it. What I usually do in these cases is adjust the backstop distance based on character's movement or speed. So it only kicks in during fast motion when the clipping is more likely to happen and those artifacts are less noticeable. And here you can see with the help of backstop, I was able to get the clause working without clipping, even at just 2 or 1 sub-steps. Another issue I want to talk about regarding runtime stability is the overly stretchy look. It's also a common problem at low iterations or low substeps. The reason this happens is that the constraint network cannot fully converge, or the constraints are only partially satisfied without enough iteration. And the denser your sim mesh is, the worse the situation gets. We usually deal with this using the long-range attachment, or what we often call the tether constraints. It works by connecting each vertex directly to the closest kinematic points. So in addition to going through multiple steps of constraints to follow the animation, it also has a long tether that connects to a fixed kinematic point directly, which help prevent the cloth from drifting too far. When setting up tethers, the most important thing is to find the proper fixed tether ends. In most cases, you'll want to enable geodesic tethers. This searches for the closest kinematic point across the surface instead of using Euclidean distance. That way, as you can see here, the sleeve won't accidentally connect to the torso. And in the latest release, we also support custom tether generation. So you can control exactly which dynamic part connects to which fixed kinematic parts. As for the cloth I was testing, I also made a small adjustment to the tether ends. Because I made the cuff area kinematic, some words will connect to the cuff. Some vertex on the sleeve will connect to the cuff. But since gravity almost always pulls the sleeve downwards, connecting to the cuff is pretty much pointless. So I select and filter out those points on the cuff and only use points on the shoulder as tether ends, which makes the long-range attachment works more effectively. This might not be the most obvious example, but the point is, if you understand how tether works, you'll know how to use them more effectively in different situations. A lot of the stability issues I mentioned earlier tends to get worse during fast character movement. So another important feature for runtime stability I want to talk about is the velocity scale. With velocity scale, you can decrease or clamp how much word space movement will affect the cloth dynamic. As you can see in the video on the right, it helps stabilize the whole simulation when the cloth component is moving at a high speed. Velocity scale includes both linear and angular control. It also helps you to clamp in respect to acceleration. This is especially useful when the character makes a sudden stop or a sharp turn to keep the cloth from lagging behind and behave unpredictably. Okay, that's the runtime stability section for today. The final topic I want to cover is a few advanced features in Chaos Clause, mainly about more accurate collision with the character and also about clause self-collision. The kinematic collider has been supported since 5.4. That means the cloth can collide with the skinned deforming body mesh, which is much more accurate than spheres and capsules. The setup used to be a little complicated, but in 5.6, you can now generate them directly inside the physical asset and assign them just like simple collisions. Colliding with the triangle mesh is pretty expensive. So if you are targeting real-time performance, there are a few optimizations you can do. First, you can simplify the mesh you are colliding with, either by using a higher load or by using the remesh or simplify tool in the skeletal mesh editor to cut down the poly count. Secondly, you don't have to apply the kinematic collider to the entire body. As you can see here, I only use it on the torso since that part is harder to describe with just capsules. And lastly, you can enable kinematic collider only for nearby characters. There are options in the collision config to enable simple or complex collision separately, and it can be set per LOD. Close self-collision is another advanced feature, and we support two types of self-collision. Sphere-based self-collision is more game-targeted. It only considers intersections between vertices. On the other hand, the point face-based solution is more accurate, but of course, it's also more expensive. No matter what type you choose, you can set a separate sub-step for self-collision, independent from the main class solver. That's a very useful optimization. Self-collision becomes really important when you are working with multi-layer clause, especially for cinematic use cases. I recommend use the point face-based solution, and you can set up collision layers to get better result in those cases. To set up collision layers, you need to select them separately and convert it into an integer map for different layers. The lower layer will push the higher layer outwards, so it's like a hint to the collision solver, help it resolve more quickly and more reliably. Okay, that wraps up everything I want to share today. Thank you so much for your time, and I hope you find it useful. Also, I want to take this time to thank our Chaos dev team. And earlier this month in Orlando, there are also talks on Chaos clause, and they are on YouTube now. So please do check them out. Thank you so much for today.